Mn by 1, F transpose is 1 by Mn. So this is an Mn by Mn matrix, FF transpose. Whereas F transpose F is a single quantity, 1 by 1. And take the trace of the matrix, that is the sum of all the diagonal elements, then that is the energy of the image. So instead of writing the energy as sum of m going 0 to m minus 1, sum n going 0 to 1, 0 to n minus 1, f square mn, you just write it as f dot f or f transpose f. Even the dot notation is not commonly used in matrix operations. So f transpose f or f prime, sometimes instead of t, the prime is used. Or outer product. Sometimes you may need the outer product to get the cross terms. If the image elements or pixels are considered to be random variables, which we said we do earlier, if the image is corrupted with noise, noise is random, so the combination of noise with image is also random, then you want to take the mean is expectation of f. So it is just an algebraic variable that you have put in these expressions, which is an mn by 1 matrix or vector, expectation of the entire matrix, not the average value, but expectation of this means you have a number of images and you are taking the average of the images, an ensemble average, or statistical expectation of the entire image. Covariance, expectation of f minus f bar transpose, which turns out the expectation of ff transpose, f bar transpose. And this is an mn by mn matrix. Now, suppose you have 1,000 by 1,000 image, which is fairly common, or your camera gives you 6K by, my camera gives me 6K by 4K. Yours may give you, I don't know, a billion by billion pixels. But if you have 1,000 by 1,000 image, which is not very big nowadays, this will be a million by million, this matrix. Well, that's going to be very huge, and you may not have the capacity in ordinary computers when you have even larger images, medical images. So these are mathematical representations to facilitate the derivation and representation of operations. You may not do it this way in computation, or you may have to take some special, develop special algorithms to compute them as needed. You may not have the storage capacity to handle this. So you have an mn by mn matrix. Along the diagonal, we have the variances of each pixel. And the other sigma 1, 2, sigma 2, 1, sigma 1p, sigma p1, sigma p2, they are the cross correlation or cross variance between various elements. So this way we get the cross terms. Sigma PQ is expectation of FP, okay, FP minus FP bar, FQ minus F bar Q. That is two different pixels. So you get the cross relationships here. So sigma PQ is the covariance between the pth and qth elements of the image vectors. Sigma is symmetric. Sigma PQ is sigma QP. The diagonal terms are the variances of the elements of the image vector of each one. But this is across a population. You need a population of images. You cannot compute this for one image. That's why we have the expectation operation. In practice, the expectation operation is replaced with a summation over a database of images. The autocorrelation matrix is expectation of FF transpose. There is no subtraction of the mean. That's all. And this is also an mn by mn matrix. And if you normalize covariance, sigma rho pq is sigma pq divided by sigma pp and sigma qq, then the diagonal elements are 1. And then you have the covariances on the other sides. And it is symmetric again. The absolute scale of variation, the sigma values along the main diagonal are in another diagonal matrix D. Then this sigma is d rho d. Sigma is this one, the covariance matrix, where we had the variances along the diagonal. When you normalize, the diagonal is 1, but you need this to keep that factor of the variance. Then sigma is d rho d. If the mean is 0, then the autocorrelation and covariance are the same, but in images, it is not common to encounter 0 mean. So using this notation, we can redefine some of the statistical properties. Two images are uncorrelated if expectation of F G transpose is expectation F, expectation G transpose. That is, the expectation can be separated. Expectation is like integration. The two can be separated out if they are uncorrelated. Then the cross covariance matrix sigma FG is a diagonal matrix, and the cross correlation phi FG is an identity matrix. They are orthogonal if the projection of one onto the other is 0. When you project one vector onto another, if it is 0, then they are orthogonal. They are statistically independent if the probability density function joint PFG is PF times PG. Then F and G are also uncorrelated. So these are some basic statistical properties expressed now using this matrix notation, which of course you would do with ordinary variables. Expectation of xy is expectation x times expectation of y, where x and y are just scalar variables. But now they are matrices representing entire images. Okay? Is that clear? Okay, now how do we apply transforms to this representation? Transforms such as the Fourier transform. So let's start with some basic 1D transform of some kind. We don't specify what it is. Let's start with a single dimensional, one-dimensional signal, f of t. And you can use continuous notation first, and then we will switch to discrete. So f of t is ak some phi kt, where the functions phi k are the basis functions, and for that they have to be mutually orthogonal. So mutually orthogonal means the projection of one onto the conjugate of another, phi kt, phi l star t dt, integrated, is some constant. If that constant is 1, then they are called orthonormal. The Fourier transform has sinusoid functions which are orthonormal. So the signal is expressed in terms of these functions with some weights ak. So ak is obtained by taking the projection of the given signal onto the conjugate of each of these basis functions, phi star k. So this is like the transform to get the coefficient values given the signal and the basis functions. So ak is the projection of ft onto phi kt. So this set of functions phi kt is said to be complete or closed if there exists no square integrable function ft for which the projection of that signal onto that function is 0. In that case, that function should also be a member. So for the Fourier transform, all sinusoids, sine, cosine, and for plus and minus frequency to infinity, plus and minus infinity, they're all included in the basis function. In the DFT, it is limited, as we will see. So ft is orthogonal to all of the members of the set of this phi kt functions, and then it is called an orthogonal or orthonormal basis set, or just basis for the transform. The Fourier series representation of periodic signals uses an infinite set of sines and cosines at integral multiples or harmonics of the fundamental frequency of the given signal. So that is an example. We will see details soon. And these functions, phi kt, all these basis function members, and the given function ft must be square integrable. That is, they must have finite energy. There are some other conditions, but right now we will only use this one condition. So suppose now you have a 1D signal as an n by 1 vector or a column matrix. We can represent transforms using n by n matrices. L. Capital F is the transform domain. Small f is the input time domain or space, whatever that domain is. L is the transform. So now you can write f equal to LF. Capital F is equal to LF. So that's a very simple representation of the transformation, but how do we write L? We need to see that now. And then the inverse transform is the original small f is L star transpose, the conjugate transpose, times the transformed space quantity. Now L times L star T must be equal to I, the identity matrix.
Sir, what about the other? Is it unitary? Is it unitary man?
Which one?
L.
The identity matrix. No. L is the transform. L is like the DFT, as you will see.
The matrix corresponding to transform. The matrix corresponding to transform.
Yes. The elements of the matrix will have values of the basis function. So if you open it up, then Fk is summation L n going 0 to n minus 1 Lkn Fn. Fn is the input signal. And Fn is the sum on k going 0 to n minus 1 L star Lk Fk. We are writing it as just L. It could be any transform, DFT, Walsh transform, Hadamard transform, and so on. So this is the forward transform, inverse transform. So now let's look at the DFT, which you're all familiar with. So for DFT, L is defined as Lkn equal to exponential minus j2 pi over n, capital N, the number of samples times Kn. N is the time index, K is the frequency index. That's the DFT kernel function, basis function. Now in the FFT algorithms, typically this is written as W subscript n. How many samples do you have around the unit circle, as you will see, or in the signal and the DFT? Exponential minus j2 pi over n, the frequency index is taken out, or both indices are taken out. It depends only on the number of samples in total in the signal and DFT. Then Lkn, the knth element in that matrix, is W sub n to the power of Kn. So Fk, the DFT, is Fn times this quantity. This is the standard DFT, right? K going 0 to n minus 1, and n also goes 0 to n minus 1, right? So if you want to write it out as a matrix, that is the DFT. This is the input signal. This is the DFT matrix, L. So what are these W's? Exponential of minus j2 pi over n times that power, 0 to n minus 1 times n minus 1. K and n going 0 to n minus 1. So the row index and the column index will go 0 to n minus 1. Now there are some advantages with the sinusoids. There is some repetition of the same values. That is how you get the advantage in FFT, by making use of periodicity and the relationship between the sine and cosine functions. So because of periodicity, Wn to the power of m times n minus 1 is the same as W to the power of minus m, or W to the power of n minus m, or any integer m. So multiplying by an integer doesn't change. And W to the power of n is equal to 1. So for a given n, there are only n distinct functions. It's an n by n matrix, n square values, but there are only n values that are unique and they are repeated. So W to the power of k sub n, those are the unique values. Others are just repetitions. There's a nice figure that was given by Hall. where you see the unit circle, that is supposed to be a circle. Is it possible to adjust the aspect ratio? Because later on, when we do shape analysis, we need to look at the shape properly. Right now, it's okay. So this is a circle. It looks like an ellipse because of the projection. So the DFTs is obtained by sampling around the unit circle in the Z domain, right? You know the Z transform. And when you go around the unit circle, magnitude Z equal to 1, then Z translates to the exponential function. And this is W using n equal to 8, W sub 8. The powers 0, 1, 2, 3, 4, 5, 6, 7. And then 0 again, the same thing happens. There are only 8 values. But the matrix is 8 by 8, 64. The same values repeat. So the transform DFT going 0 to n minus 1, the input signal going 0 to n minus 1, you only have these values. Wn to the power of 0, 1, 2, 3, so on, n minus 1, and the same values repeat. So that is the DFT matrix. Now we don't have 64 or n by n values, we only have n values. Specifically for n equal to 8, 0 to 7, this is the DFT, 0 to 7, that's the input. And here you have the W function, the sub 8 has been removed. And it's only to the power of 0, 1 through 7. So that's the DFT matrix. Now you can write the one-dimensional, this is one-dimensional DFT of a 1D signal using a matrix. And there are some papers on FFT algorithms using matrix notation to show that FFT can be achieved by some properties as we are seeing now. Is that clear? Okay. So now let's go to 2D. FKL, the transform is given by FMN, the input, multiplied with this kernel function or basis function, which now has 4 dimensions. In the 2D case, the kernel function had 2 indices. The input has 1 index, but the transform has 2 indices, k and n, n for time, k for frequency. Now, the input has 2 indices, m and n, for x and y coordinates. The output has kl for 2 frequencies, horizontal and vertical frequencies. So the kernel function has 4 indices, m, n, kl. So if you have a 3-dimensional image, then the input image has 3 dimensions. There will be 3 frequencies. The kernel function will have 6 dimensions. So FKL is written as FMN times pi mn KL. Why is only that turning off? Everything else is okay. Is it getting heated or? Okay. And FMN, the inverse transform, is FKL times some other function psi, mn KL. So what are these? The forward transform kernel and the inverse transform kernel of some transform. We assume that they are separable, which means phi m KL can be written as phi 1 mk, one input variable, one output variable. That is one space variable m, one frequency variable k. Phi 2, another space domain n, another frequency variable l. And symmetric if phi 1, phi 2 are the same, like in the DFT exponential. Then you can compute the 2D transform in 2 steps, one along the rows and the other along the columns. You take the result of the first transform. So first one is F1 ml is FMN times phi nl on n. This is a function of n and l. So this is the output of the first transformation, which has one input index m, one output index l. Now take that and apply the second function phi and k, you get FKL, the final transform output. In the case of the 2D Fourier transform, phi m n k l is exponential minus j2 pi over n m k plus nl. We assume n by n square image, and that is separable like this. So this is like a 1D DFT function. Just the index variables are different, right? Then the 2D DFT may be expressed as capital F, the transform is WFW. Lowercase f is the input image, capital F is the transform, Fourier transform, spectrum. So F is the input n by n matrix, W is a symmetric n by n matrix. We will see another representation where it is different. Okay, please note here, these are all n by n matrices. We haven't done the column ordering in this case, or row ordering. And Wn to the power of km is this exponential function which we have seen already. There is periodicity of Wn, so this matrix W has only n distinct values, as we have seen. Now there is pre-multiplication and post-multiplication for first column or row transformation, then transformation on the other dimension. Row or column, whichever one you want to do first. So WFW. But these are all n by n matrices. At the beginning I said we will convert the image to n square by 1. But right now in this formulation, the image is still kept as an n by n matrix. And the transform is also n by n. Whereas for the 1D case, we saw for an n by 1 signal, the transform matrix was n square by n square. N by n. So the DFT matrix is symmetric, with its rows and columns being mutually orthogonal. The sinusoidal functions are mutually orthogonal. So WMK times WML star is conjugate, is equal to n. So that's why you have a 1 over n. If you put the 1 over n, then they become orthonormal. So then W inverse is 1 over n W star. You take that n and put it there. Then the inverse transform is 1 over n squared W star F W star. So the forward and inverse transforms are written using the same matrix W but conjugated. And they look similar, WFW. There is this factor 1 over n squared. In most books you will see 1 over n for the forward, 1 over n for the inverse, just for symmetry. But in most 1D cases, you put the 1 over n only on the inverse transform. But here we have 1 over n squared. So there are a number of transforms that may be represented in this format. F, the transform is AF. Small f is the input, capital F is the output of the transform. A is some matrix. Depending upon the transform, the matrix will be different. So the computational requirements may be reduced by taking advantage of the properties of the basis functions. So the DFT matrix in particular may be factored into a product of 2 log n, natural log n, of sparse and diagonal matrices, and that reduces the computation because sparse matrices have many non-zero elements and a diagonal matrix has only values along the diagonal, the others are 0. So by reducing this matrix that may have various real values into a series of matrices that are sparse and diagonal, you can reduce the number of computations, and that forms the basis of the FFT algorithm viewed in a different way. The original Cooley and Tukey algorithm was not developed this way, but there are other papers showing matrix derivation of the FFT algorithm. To give you another example, the Walsh-Hadamard transform is commonly used in image processing. It could be used in signal processing also, but it's not so common. Now here, the set of 1D Walsh functions is defined using this iterative relationship, phi sub n, the nth function of x is some variable, is phi 2x of n over 2. This is the order of the function. And phi n over 2x minus 1, depending on whether we are in the first half or the second half, and minus if n is even. So this is the integral part of n over 2. I'll show a picture which makes it more clear. Phi 0x is defined as 1. Phi 1x is plus and minus 1 for half the interval. The nth function is generated by compression of the function phi n over 2 into its first half and plus or minus phi n over 2 into the second half, like this. N equal to 0, all the values are equal to 1. So these are the first 8 Walsh functions sampled with 100 samples. There are 100 values here over the interval 0 to 1. So this is half of that index, time or space or whatever that is. So how do you get the first one? N equal to 1. You take this, compress, and you put it in the first half. And take that and compress and put in the second half. This is odd, so you reverse this, plus and minus 1. And for 2, you take this, 2 over 1, 2 over 2 is 1, so you take that, compress in the first half. And take that and compress and the second half, reversed. And so on. So for n going 0, 1 through 7, you get this. They're not sinusoids, they are rectangle functions. They're not squares. Some of them are not square. Okay? So Walsh functions are ordered by the number of zero crossings in that interval called sequency instead of frequency. It's not a sinusoid, so you don't call it sequency. No zero crossing. 0. 1 zero crossing. 2, 3. 1, 2, 3, 4. That's 5. 1, 2, 3, 4. This ordering changes depends upon the definition you use. So this has 5 and this has 4 zero crossings. So the sequency numbering and the way you generate using this rule, the order will be different. I'll show another definition. If the Walsh functions with the number of zero crossings less than 2 to the n minus 1 are sampled with n equal to 2 to the power of n uniformly spaced points, we get a square matrix representation that is orthogonal. I'll show you that. Rows are ordered with increasing number of zero crossings. The ordering of the Walsh functions varies with the formulation. That's what I wanted to say. I started counting, but 4 and 5 are switched with that formulation. The matrix is this, plus and minus 1. No zero crossing. Here 1 zero crossing, and so on. There. So because this has just plus and minus 1, you only have addition and subtraction. So computation is simpler. Previously, in the 60s and 70s, computers were not as fast as what you have now. And the Fourier transform used to take substantial amount of time. So there was interest in other types of transforms where the computation could be reduced, such as this, where it's only addition and subtraction. Or the DCT, discrete cosine transform, for image processing. For signals, computation was not a big issue. When we started our work on digital image processing, we were working with little images, 64 by 64, 100 by 100, and so on. So in my book, I still have some examples that are fairly small images. But the mammograms that we have processed in our research work are 4,000 by 4,000 pixels for one image. 3D data sets of computed tomography, that depends on the resolution used. There could be 50, 60 to 100 slices in the chest and abdomen. And each one could be 512 square, 1,000 square, whatever. Depends on the radiation dose used and the resolution used. So then, the Walsh transform of a 1D signal is f equal to AF. like we saw for the FFT case. Now this is the matrix representation. There is another formulation, I don't want to read this, using the bits, the p bit in the p-bit binary representation of M. You read that later on. To read that, it makes no sense to read that. -1 to the power of something where the bits are used. But I think that is clear, and this is clear. This is, I think, for computer scientists. The major advantage of the Walsh transform, the kernel has only plus and minus 1 values. Addition, subtraction. Identical operations in forward and inverse transformation. So except for ordering of the rows, the discrete Walsh matrices are equivalent to the Hadamard matrices of rank 2 to the power of n. A2 is 1, 1, 1, minus 1, and A2n is an, 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 minus an. So you repeat the same thing. Take this, repeat, repeat, and minus here, and you get a matrix of double that size. Then if you define A is 1 over root n of an, the Walsh-Hadamard transform of a 2D function may be expressed as f equal to AFA, both ways, which were forward and inverse. So all matrices are n by n. Okay? So these are the first 64 Walsh-Hadamard 2D basis functions. Black is -1, white is +1. So just one change here. And here you get a chessboard pattern. Increasing horizontal frequency, increasing vertical frequency in some manner. Compare this with the sinusoids I showed earlier. I wanted to create these patterns. A few books have this, not many books have these pictures. I spent some time creating these in MATLAB. Hopefully they illustrate the nature of these functions. What do they look like? Any questions about this? You may need to work through this later on at your convenience. I'm sorry?
Types of transformation was later on, but before that, for a single image, we did a transformation many times. Why is it necessary to do the transformation many times?
Why is it necessary to do the transformation?
Many times.
Many times.
Yeah, before the topic that we covered, types of transformation was covered. Before that, we did transformation 3 times a day. Why should we do 3 transformations?
I'm still not understanding the question. Why are we studying transformation again? No.
Why are we applying transform to the image more than once?
Where are we applying it more than once?
We did it. Because we applied at least 3 times.
I expressed the transformation in a different way. We use the conventional array notation of transformation. We are not applying it again. This is simply a different formulation, right? So here, this f, small f, is still the original image. This is simply a different formulation of the transformations we talked about earlier. I showed the Fourier transform. I showed the Fourier transform of pictures. I didn't say how we computed the Fourier transform, right? I just assumed everybody knew that. But now we are looking at how the Fourier transform, not how it is computed, but how it is formulated. We are looking at the details. Is that what you wanted to know? Yeah. So we are not repeatedly applying. Sometimes we do have application of the transform multiple times in a whole algorithm where you go one transform to another and back and forward. Like in homomorphic filtering, I'll show you later on. But here we are simply looking at formulations in the function format fxy or f capital F uv, or in the discrete notation Fmn Fkl, or in the matrix notation as F equal to AFA, and so on. At the beginning I showed examples. Now we are backtracking a bit and looking at the representation. So I'm mixing the two so that we don't do all of this mathematical material at the beginning and leave all the examples to the end. So I'm mixing that. Is that what you wanted to? Okay. Any other question? We are doing this, as I mentioned at the beginning today. This formulation is required, or I shouldn't say required. This formulation facilitates the derivation of optimal filters. At the beginning, we did not look into optimization of filters. We just said this is the transform, and we applied some filters using space domain operations and frequency domain operations. We didn't say how we got to the frequency domain. And we didn't say they are optimal. We said try this, try that. If you like it, fine. If not, try something else. But next we will see, after this, optimal filters. In order to optimize a filter operation using sub-optimization procedure, derivatives are required, expectation operations are required. Then this formulation facilitates that kind of derivation. That's why I'm bringing this here. If we don't see this, it will be hard to show the Wiener filter, for example. Okay? Now convolution. How do you represent convolution using matrix representation? Earlier we saw convolution, that one signal is kept the way it is, the other signal is reversed. If it is image, you have to reverse this way and that way, and then multiply and shift and get the output for all shift values. But how do you do it in this matrix notation? So I called it matrix vector multiplication, but it is matrix multiplication. A vector is also a matrix. So let's start with a 1D representation. Gn is f alpha hn minus alpha. F is the input, h is the impulse response, and alpha is some temporary variable, and minus alpha represents reversal of h, and n is the shift, and the output is given for that location. Assuming causality, alpha starts from 0 and goes to n only. If you want, for the sake of generality, you could write minus infinity to infinity, but causality is usually included when you go 0 to n. If the input is given over n samples, we could represent the output over that range 0 to n as g equal to hf. So this is the matrix representation for 1D. F is an array like that, to 0 to n samples. G is the output. This matrix H now is computed using the values of the impulse response. Matrix multiplication, you take this and put on top of this row and multiply F0 times H0, and the rest are all 0. So G0 is H0, F0. So the matrix has only the first element of the impulse response. For the second one, you have the first H0 and the H1, causality. And then 0, 1, 2, and so on. Then at the end, you have all the values. So what do you get? Gn is F0 times Hn, F1 times Hn minus 1, and so on. So write that and check with the equation, and that is correct. So H now, this matrix, it is not diagonal, but there is a whole bunch of zeros there. It is said to be Toeplitz-like, but I'll show Toeplitz matrix later on, which gives some computational advantages because of these zeros. A Toeplitz is a square matrix where the elements are equal along every diagonal, but that's not the case here. This is equal, that is equal, and so on, but the other side doesn't appear that way. There will be zeros in the lower left portion here if Hn has fewer samples than Fn and Gn, and H is then said to be banded, zeros there and zeros here. the impulse response will not be long. Of course, there are filters with infinite impulse response, IIR filters. But if your filter is an FIR, finite impulse response filter with only 3, 4, 5 samples, but the input is long and the output is also long, then this matrix will only have maybe H0, H1, H2, and everything else is 0. You still have to write an n by n matrix for multiplication, right? So G equal to HF is convolution. The projector is getting tired of my equations. If the impulse response has a finite duration of m plus 1 samples, FIR filter, then you may center the impulse response at the point where you're getting the output, both sides. Then you write the index as alpha n minus m over 2 and plus m over 2, f alpha h n minus. It's the same convolution, but now the index doesn't run 0 to n, but it's a moving window operation. The signal is long, you're computing the output here, and the window is centered there. The impulse response is centered there. You can also change variables and write that way. I won't read that. So here also you can write it as GF, but the matrix has to be written this way. I'm sorry, it's a little difficult to read that, but so you have hm over 2 to h minus m over 2, the impulse response. Now having positive and negative indices, h0 is in the middle, and that is shifted for every row. So each row is a right shift of the previous row. The input is also written going from minus m over 2 to n plus m over 2. If it is causal, then the negative index values will be 0. The output is obtained for 0 to n for causality. But input may not exist for negative values. This is simply notational convenience. Although these are causal, you can impose causality on this. So H is now said to be banded and toplets-like. Each row of H except the first is a right shifted version of the preceding row. And M is less than N. FIR filter has a small short impulse response. The input could be much longer, and the output. Okay? So this is banded in the sense there are zeros there, there are zeros there. These are not diagonals, but the same values occur in bands. And each row is a right shift. The same values occur here, but with a shift to the end here. There is another type of convolution known as periodic or circular convolution, which is what you get when you use DFTs. When you take the DFT and multiply and come back to the time or space domain to achieve convolution, then what you get is not linear convolution, but circular or periodic convolution. But you can get the equivalent result by zero padding. Now in this case, periodic or circular convolution, all the signals are assumed to be periodic. As I mentioned earlier, when you sample a signal, sampling implies periodicity of the spectrum. The frequency domain function becomes periodic. When you compute the DFT, you're sampling the Fourier transform. So sampling the Fourier transform implies that the time domain function is also periodic. So the DFT pair, forward and inverse, the signals are periodic going around the unit circle in the Z domain. So if you go round and round, you get the same thing. You're sampling around the unit circle. So all signals are periodic. But if you have a non-periodic signal, you simply say, well, it is one period of that periodic signal. I don't care about the other periods. I'll just take one period, let the others be there. Theoretically. Theoretically, yes, but sometimes there are implications of aliasing errors if you don't take care. So it is not simply some theoretical stuff, but there are implications of aliasing unless you take care with adequate number of samples. So if they're all periodic, shifting is periodic. Linear shifting, you shift each sample at a time and it keeps going. Periodic shifting, if this is the period, if you shift, the sample that goes out will come back here, shift again, another sample comes here. So you're always having n samples. And what goes this end will come back the other end. Some books say it's like having samples written on a drum. If you rotate the drum, the same samples keep appearing. So GP and P is periodic. FP alpha, HP, n minus alpha mod n. So that index has to be periodic, only between 0 and n minus 1. So the shift is given there, and alpha going 0 to n minus 1 over one period. Excuse me. Did we say we go 9:30 to 10:30 or 11? 10:30. Okay. Okay. Oh, 2 more minutes. We started 5 minutes late. The result of periodic convolution of two periodic signals of n samples each is also a periodic signal, whereas the result of linear convolution would have two n minus 1 samples. Linear convolution gives you a longer output because you keep shifting until there is no overlap. And the shift has no limit, whereas here the shift has a limit because of periodicity. So that's an important property to remember, that the linear convolution of two signals with n1 and n2 samples will have n1 plus n2 minus 1, or in this case 2n minus 1 samples. Periodic, n1, n2 cannot be different. The two signals must have the same period, real or assumed. And then the output will also have the same period. But linear will have more. So how do you get that? Periodic convolution may be used to achieve the same result as linear convolution by padding the signals with zeros, so that you increase the duration to at least 2n minus 1. If you want to have more, go ahead with more, but it will be a waste. There won't be any more samples. So just pad with zeros. So you must use 2n minus 1 samples. So implementing convolution as the inverse DFT of the product of the DFTs of the two signals implies periodic convolution. Otherwise, if you don't take care of this, you get some wrong result. Zero padding will be necessary or required if linear convolution is desired. In the case of a causal linear shift invariant system, what you want is linear convolution. Periodic convolution may also be expressed as G equal to HF. F has 0 to n minus 1 samples, G has the same. Now the impulse response is written with H0, and what was shifted out will come back here, H1, 2, so on, Hn minus 1. You shift, H0 goes there, H1 that was here will come here, and so on. At the end you get 0, 1, n minus 1 in reverse order because of the reversal in the convolution integral or sum. So if you want, you can take this, F0, multiply with this, F0 Hn minus 1, F1 Hn minus 2, and so on, Fn minus 1 H0 is Gn minus 1. Take the convolution in sum or integral and work it out. That works. Now each row of H is the right circular shift of the previous row, including the end. Shift this, H0 comes here, which is that. So bottom to top also right shift works. And this is called a circulant matrix. It is a square matrix. It is a circulant matrix because each one is shifted in a circular manner and also bottom to top. So that is a nice representation of circular convolution or periodic convolution. The same G equal to HF. The variation is only in this. How do you formulate this matrix H? And in 2D we will see how to do that. So we'll stop here. We'll take a break now. Just a moment. Yeah? You have to speak up. There's fan and everything.
In practical implementation, while performing circular computation using FFT, how do we make sure that the output matches the exact result of the linear column?
I'll give you some numerical examples soon. All you have to do is pad with zeros. And then you extract the required portion. In the output, you will have, if you pad with more zeros, the non-zero values will give you the output and the other values could be ignored. There will be zeros. I'll show you some numerical examples. It is possible to achieve linear convolution using this procedure. And I'll show you the matrices. Okay?
There's one more doubt from the previous one. Can the watch function be used in ultrasound imaging to less down the spicules and also maintain the edges?
The watch transform is just a transform. What you do with the transformed function is up to you. You can achieve filtering. I have not used Walsh functions for filtering. Walsh-Hadamard functions have been used more for data compression and so on. Filtering is typically done using the Fourier transform because you have a better understanding of the frequency. Here you have sequency and it's a little harder to correlate sequency with the nature of noise. So I have not seen good examples of filtering using the Walsh-Hadamard transform. But I have read papers where it's used for data compression. What you do with the transform is up to you, whether ultrasound or any other image. How you filter depends on how you interpret those components. And since I have not used them, I cannot tell you how to interpret the frequency components of the Walsh-Hadamard transform.
Thank you.
It's a theoretical nicety. I have not seen many papers where it's been used in practical applications except for data compression.
So learning purposes trying to use it, and the learning purposes trying to use it. That's it.
Okay. Any other question or comment?